Today I will start with the discussion of the same topic, that is topic 3, where we are discussing dye sensitized solar cell, quantum dot sensitized solar cell, perovskite solar cell and tandem solar cell. So, in the last class I briefly reviewed the dye sensitized and quantum dot sensitized solar cell with some questions and answers. Now, we will look some review questions of perovskite solar cell and tandem solar cell. So, as we have discussed regarding perovskite solar cell, let me just briefly tell you again about this. The perovskite, particularly inorganic, organic, halide perovskite, which actually have placed a very important role in the development of perovskite solar cell. And as we have seen, it was introduced in the literature in 2009, and by 2014-15 it showed a huge improvement in the efficiency with development of different materials, and almost, as it is reported, almost 20 to 23% of efficiency was reported, and therefore, there are a lot of promise which people have found in perovskite solar cell. And generally, this perovskite solar cell architecture or configuration is same as what we have discussed about dye sensitized and quantum dot sensitized solar cell, with little more versatility in the perovskite solar cell, that you can either have perovskite solar cell in the mesoscopic configuration that we had in case of dye sensitized solar cell and quantum dot sensitized solar cell, and there is another configuration which is thin film configuration. And the importance of perovskite material, particularly this inorganic, organic, halide material, is that one can tune band gap of the material by changing either halogen element or by changing the organic element, or organic compound in this structure. And therefore, it is important that the light absorption capability of this material increases, eventually giving very high efficiency with very high the open circuit voltage for perovskite solar cell. Of course, there are some issues which I discussed related to stability of the perovskite solar cell, and this is one concern regarding perovskite solar cell. Otherwise, the deposition process or the growth process or the synthesis process of perovskite solar cell is quite simple. Okay. So, let us look at some questions on perovskite solar cell, and then I will go to some questions of tandem solar cell. So, the first one is, why perovskite material is a good choice for solar cell? So, what we have seen that perovskite material, particularly the inorganic, organic, hybrid perovskite which are used in the perovskite solar cell, have different important properties which actually give them a very strong, make them a very strong or potential candidate as a solar cell. One important property is low excitonic binding energy, Second is high absorption coefficient of light, and then it can be over a large the spectrum of solar light. So, higher absorption coefficient third important property of perovskite material is tunable band gap. During my lectures, I told you about how this tunable band gap is possible in perovskite material. Today also I will just show you with different example how one can tune the band gap of perovskite material which are used in the perovskite solar cell. And number 4 is the transport of charges. Okay. So, one can have this perovskite material where the electron, that is the charge carriers, can move at quite a far distance without the recombination. So, there is a capability of perovskite material and which eventually increases the open circuit voltage of the perovskite material, which is used in the solar cell, perovskite solar cell, and overall it gives a very good choice for a good or highly efficient solar cell when we design a perovskite solar cell. Now, the second question is, what are the basic differences between sensitized and thin film configuration of perovskite solar cell? So, as I discussed in my lecture that there are two configurations which are possible in perovskite solar cell. One configuration is directly what we have seen, similar to dye sensitized and quantum dot sensitized solar cell. So, that is the sensitized, or you can say mesoscopic configuration, where we have a mesoscopic TiO2 okay. And then on here so these are perovskite crystal, this is TiO2, actually perovskite crystal embedded in TiO2, and then on top of this we have a whole transport layer HTL, and generally the whole transport layer which is used in this solar cell is pyro omitted. Okay. And then here we have an TCO, okay, and we can also combine this and call it this electron transport layer and TCO, and then we have here one more layer metallic contact. Okay. So, this is the mesoscopic configuration of a perovskite solar cell, where the perovskite crystals are anchored in TiO2, okay, and then when light falls on the perovskite solar cell or perovskite material, electron and holes are generated, and the holes are transported through the hole transport layer or spirometer to the circuit, outer circuit through a contact, and electrons which are generated in the perovskite, they follow the path like it follows the path of the TiO2. It is injected in the TiO2 and then it goes through a contact layer of transparent conducting oxide. So, this is one configuration. This is known as sensitized configuration or mesoscopic configuration, and let me show you the another configuration. Another configuration where we have a thin film of perovskite. So, there is no TiO2 in that. Say a film, and this is active the medium for generation of charges, and then we have similarly what we had in other case. A hole transport layer which is spirometered and then a contact, metal contact. Okay. And then here we have an electron transport layer or ETL, then we have a TCO. So, the difference in these two configurations is that here we do not have the mesoporous TiO2, we have only a perovskite film, and when light falls on this perovskite film, it generates electron and hole, and then holes are transported through the hole transport layer which is generally spirometered, and then it goes across a contact. Okay. And the electrons which are again generated in the perovskite layer, they follow the other path, it goes to an electron transport layer and finally through the transparent conducting oxide electrode to the outer circuit. Okay. So, in one case, in the first case what we have seen, the electrons which are generated are injected to TiO2, after that they follow the path, and in this case there is no TiO2. So, there is no injection of electron and it directly follows the path of electron transport layer and the transparent conducting oxide. Okay. So, let us see the third question. What are ETL and HTL in perovskite solar cell? So, I have already shown you what is ETL and HTL. Okay. One is electron transport layer, another is hole transport layer, and what role they play. So, it is simple that electron transport layer actually allows electron to transport through this layer, and through the electrode it goes to the outer circuit. Okay. And the hole transport layer is basically it transports a hole which are generated in the perovskite material. Okay. So, through the hole transport layer like spirometered, it goes through the outer circuit and flow in the circuit. So, this is the role of ETL and HTL of a perovskite solar cell. So, now let us again look at this perovskite material. So, as I mentioned, that perovskite material has, that one can have a tunable band gap of perovskite material, and the question is for AMX3, this is the typical nomenclature of a perovskite solar cell which are used in perovskite material which are used in perovskite solar cell. The band gap tunability is an important feature. Illustrate it with an example. So, I have taken an example and this is an illustration. So, now you can see that how this band gap varies. So, let me take the first example which is MaPbBr3, Ma methyl ammonium, and lead and bromine. So, if you look at this particular the perovskite material, its band gap is 2.3 electron volt. Okay. So, now what one can change? One can change this halogen, this bromine by iodine, and it is MePbI3. Okay. So, just change the halogen element here and immediately you can make a significant change in the band gap and it becomes 1.55 electron volt. So, now you change this methyl ammonium group Ma by Fa, okay. Rest other things you keep same and then the band gap slightly reduced, it is become 1.5 electron volt now. So, what we have seen in these three examples, then first I change the halogen, okay, and then we have seen a drastic reduction in the band gap, and then if you change the organic part, you again see that there is a change in the band gap. Now, there is another example where you can consider MaPb1 minus X SNX I3. Okay. So, that means your methyl ammonium is there, and now what you are doing? You dope some tin in lead. There is an approach as I mentioned, that is lead is toxic, people are trying to replace it by other element like tin is one important element, Sn is one important element which can replace lead, and then we can have a different atomic composition of lead and tin and see how the band gap varies. Okay. So, now I take the X 0.25. So, here Ma and the halogen they remain same. Okay. So, I start with X 0.25, the band gap is 1.24 electron volt, and then 0.5 X the band gap becomes 1.17 electron volt, and 0.75 also the band gap is more or less same 1.17 electron volt. Okay. But now, if I go to full only tin Sn, there is no lead, that means lead is completely replaced by tin, then the band gap becomes 1.3 electron volt. So, you compare this one and this one, here the difference is this metal. So, lead is replaced by tin, and when we look at the band gap of MaPbI3, we see that the band gap is 1.55 electron volt, but when we look at this MaSnI3, that means lead is completely replaced by tin, the band gap becomes 1.3 electron volt. So, this example clearly shows how one can tune band gap significantly from a range of 2.3 to 1.17 electron volt, and that is important as a material of solar cell, and therefore, perovskite material, particularly inorganic organic hybrid perovskite material, is extremely important in solar cell science and engineering. Now, the next question, in energy diagram of a PSC, show all electronic transition path. So, we know that when light falls on a perovskite solar cell, it actually generates electron hole pair in the perovskite material, and then if I have say let me consider the mesoscopic configuration, that means there is TiO2, okay, and then there is electrolyte. Okay. So, in this case, if we look at this, so this is perovskite, this is conduction band, this is sorry. This is valence band, this is conduction band, and then I have another energy band here for TiO2, and then I have energy band here that corresponds to E redox. So, this is actually conduction band, minima you can say, or conduction band edge of TiO2, and this is the redox level. Okay. So, if we look at the transition, then the first transition is when light falls. Okay. So, hole and electrons are generated. This is path 1, you can see, all right. So, electron is injected on TiO2. So, this is part 2. So, this is the injection process, okay. And then these are actually the process which are happening, and then this whole actually sorry, this is not E redox. This is actually the energy level of spiro, that is spirometer, that is whole transport layer. So, the third transition is hole going to from valence band to the this the whole transport layer, that is spirometed. And then we can see that this is transition 3, this is whole transition, and then we have recombination. So, this is path 4. So, it is a direct recombination of electron recombining with hole, and this is another recombination path, this is 5, okay. And this is another recombination path, this is 6. That means, the electron falling back on the valence band of the perovskite. So, there is a recombination or electron following the path from the conduction band of TiO2 to spirometered, and there is another recombination process. So, this is the total the picture of transition, transport of charges, or the the transition of electron as well as hole in the perovskite material when or the perovskite solar cell when it is illuminated by sunlight. Okay. So, now let us look at what are the synthesis process of perovskite. So, I already discussed with you that synthesis of perovskite is very simple, and popularly there are two techniques when the way one deposit the perovskite film, and it is by spin coating method in general, but one can follow two processes in spin coating method. One is single step method and another is double step method. So, the question is comment on the difference between one step and two step method of growth of perovskite solar cell. Okay. So, now you can see that one particular example which is shown here. So, this is a solution that is dissolved in DMA, PbI2CH3NH3I3 solved in DMA, and then by you simply put a layer of this on a substrate and do a spin coating. So, this is a single step. So, you actually coat the entire this PbI2CH3NH3 on the substrate whatever is used to grow the perovskite material. This in the double step method you make two separate precursor solution where PbI2 in DMF and CH3NH3I in IPA isopropyl alcohol. So, this is a TiO2, on TiO2 you coat it, do a spin coating. This is now on top of PbI2. Once PbI2 is grown on TiO2, then you drop this solution of CH3NH3I3 dissolved in IPA and coat on top of PbI2, eventually making CH3NH3I, okay, and finally CH3NH3 PbI3. Okay. So, these are the basic difference when we talk about single step and double step method of coating perovskite. Now, I come to the last point, that what are the question, what are different factors those can hamper the stability of perovskite solar cell. So, I discussed in detail. Let us look at what are the different components that actually destabilize the perovskite material and eventually reduce the stability of the perovskite solar cell. So, what we have seen, there are something called structural deformation, there is something called thermal instability, there is something called moisture in oxygen, chemical stability, UV exposure, and there are some sealing issues. Okay. So, these are the all factors which play together, and therefore, the stability is an important issue in perovskite. Along with that, the most important metallic element or most common metallic element which is used in the perovskite material is lead, which is toxic. So, apart from this the stability issues, which we see here, that are the toxicity issue, particularly with Pb. Okay. So, what we have seen in perovskite solar cell, although it is highly promising that you have quite high efficiency, but because of the stability issue and toxicity issue, the perovskite solar cell is still facing problem. Although lot of research work is going on how to make this perovskite solar cell stable, and the structural factor, there is a structural factor which one can consider, calculate and design the material, okay, which is also known as the tolerance factor for perovskite solar cell, and try to optimize that tolerance factor in order to make a stable structure, and also one has to keep this perovskite material slightly sealed from this environment effect. Okay. And then of course, if you replace lead by other element like tin, as I mentioned previously, one can also get rid of the toxicity, but then again the question of efficiency comes. So, the research is going on in this direction to get an important to take care of all these issues and make an important approach or potential approach to have a higher efficiency of a perovskite solar cell, retaining for a longer duration. Okay. So, now I go to the higher efficient the multi-junction or tandem solar cell. Alright, so the question comes first that name some processes by which SQ limit can be overcome. So, we have already seen that Shockley-Queisser limit. If I just you recollect that what we have discussed during Shockley-Queisser limit, what we have seen that in case of a junction solar cell, okay, this is a typical structure. This is P side, this is N side of the solar cell, and then when light falls on this, which we see that this is the band gap energy, and the light which are having energy less than the band gap energy, they are transmitted. Okay. So, this is one loss factor is known as transmission loss. Now, the light whose energy is more than this band gap energy, they generate charge carriers, but these electrons they fall back on the conduction band, leading to another loss which is known as thermalization loss. And the the photons, these are all photons whose band gap, whose energy is same as the band gap energy of the solar cell material, they generate an electron hole pair which are known as photo generated charge carriers, and they are useful. Now, considering these losses like transmission loss, thermal loss, and there are many other losses which you consider a junction, there are some other losses, okay, losses due to interface, losses due to recombination. Considering all the losses, the SQ limit as we discussed earlier gives us a maximum limit of approximately 33% efficiency, and therefore, a question arises that how to overcome this limit. Okay. So, what we have seen when we talk about crystalline silicon solar cell, the efficiency is good. I mean, one can say around 22-23% efficiency or approximately 25% efficiency. Perovskite solar cells are also quite efficient, but the problem with silicon solar cell is it is a highly involved fabrication technique, and perovskite solar cell the issues are with the stability. Okay. And of course, both of them, I mean either of them, they were not also able to reach even the SQ limit of efficiency. Okay. So, therefore, some physical processes are required in order to overcome that problem. So, what are the different processes which we had discussed? One is Number 1 is multiple exciton generation, MEG. So, this we have seen is possible in case of quantum dot. Okay, what is multiple exciton generation? Multiple exciton generation is that when you send a single photon, it can generate 2 pairs of charge carriers, it means 2 electrons or multiple electrons. So, that is called multiple exciton generation, which can improve the efficiency, at least theoretically. The second approach is up conversion and down conversion. Up conversion and down conversion. Okay, what is the meaning of up conversion and down conversion? The meaning is that you coat a material as a up converting. Okay. So, suppose you have the band gap of the main material which is used for solar cell, and the light whose energy is the lower than the band gap energy, then you can have a material coating on top of the solar cell material which can take up this energy. Okay. And therefore, that it reduces the transmission loss and the photo generated charge carrier increases. And similarly, the down conversion is that if you want to reduce the energy of the light, okay, and make it equal to the band gap energy, and to generate the charge carriers or photo generated carriers, you have to use another material for down conversion. So, there are several materials people have done research as a up converter and down converter, and this is a process by which one can have higher efficiency and which can also overcome the SQ limit. And the third one which we have discussed is the tandem configuration. Okay. And what we have seen in case of tandem configuration, one can go to very high efficiency, even as we have seen, as the prediction is almost reaching up to 50% efficiency of solar cell. So, what is tandem configuration? Tandem configuration is typically that you have a lower band gap material or solar cell, say typically silicon, which is having lower band gap, and on top you have higher band gap material, so that you can absorb both high energy and low energy photons in one particular configuration. So, we will see few more questions related to this tandem solar cell. So, what are the important difference between 2T and 4T configuration of tandem solar cell? So, what we have seen, the tandem solar cell can be of two important configuration. One is 2 terminal configuration, another is 4 terminal configuration. So, what happens when we have 2 terminal configuration or 2T configuration? We have one cell which is the higher band gap solar cell, and then another is lower band gap solar cell. All right. So, this is a solar cell, higher band gap, and this is lower band gap, okay. And they are monolithographically lithographically they are fabricated. So, they are completely in contact with each other, okay. And therefore, what you get in the output terminal, you get a voltage output. Okay. So, one important thing is that you have this higher band gap material which actually absorb the high energy photons, or I can say let me write it high energy photon or say blue photons, and the low energy photons or red photons, they are transmitted through this and they are absorbed in the lower band gap. Okay. A typical example is lower band gap is silicon and higher band gap is perovskite solar cell. Okay. So, they are integrated, and therefore, the important thing is that you can have a very good matching between these two solar cell, provided they are also electrically matched. Okay. So, the flow of charges should not be hindered in the interface. All right. And then you get the VOC or open circuit voltage from the entire structure. Okay. This way you can make a relatively cheap solar cell as compared to 4T configuration, which I am showing now. This 4T configuration is that you have higher band gap solar cell and you have lower band gap solar cell. They are not lithographically grown or integrated, they are individual. Okay. So, this is higher band gap, this is lower band gap. Okay. Then you have individual so, you have VOC1, VOC2 and you actually stack them. Okay. So, this actually reduces the problem of current matching which was otherwise there in 2T terminal. In 4T terminal or 4T solar cell, 4 terminal tandem solar cell, you do not have this issue because they are not integrated lithographically, they are separate stack. Okay, and they are mechanically connected or electrically connected outside, and they have two different VOCs, one gives the VOC 1 and another gives VOC 2. Okay. But the disadvantage with this is that it is costly, the 4T terminal. However, if we look at the efficiency, they are more or less same whether it is 2T or 4T. Now, coming to next question is that a silicon PSC tandem solar cell EQE, that is quantum efficiency versus wavelength is shown below. Explain the graph. So, you can see this is perovskite and this is silicon, and that is what we generally use for designing a tandem solar cell. Okay. So, perovskite is higher band gap material and silicon is relatively lower band gap material. So, if we look at this wavelength range, the perovskite shows a very high quantum efficiency at lower wavelength regime or higher energy regime, and silicon shows a higher quantum efficiency at higher wavelength regime or lower energy regime. The reason is very simple, because perovskite has higher band gap. So, it absorbs photons of higher energy or lower wavelength, okay, and therefore, its quantum efficiency is high for lower wavelength photon, okay, as it is shown here. And silicon, it absorbs photons of higher wavelength, that is lower energy, and therefore, the quantum efficiency of silicon in this tandem configuration is higher for higher wavelength photon, and this is demonstrated in this graph. And now, let us look at how actually this a tandem solar cell typically made up of perovskite and silicon looks like. So, a typical configuration of silicon PSC solar cell is shown below. Explain function of each layer. So, let us look at the solar cell again. So, here we have a p type silicon, here is n type silicon. So, the lower or the solar cell which is in the below is lower band gap, as I mentioned. So, lower band gap is a junction solar cell like p-n junction solar cell made up of silicon. Okay. So, the role of p-n junction is to generate the charge carriers when photons fall on this junction, okay, and then transport the charge carrier also towards the back electrode, and this eventually transfers electron to the outer circuit. So, let us now look at the other layer. So, this is perovskite which is used in the top cell. Okay. Perovskite, say it is a thin film configuration perovskite. So, this perovskite is used for generation of charge carrier when light falls on the perovskite material. When charge carriers are generated, it also transported through the perovskite, and then it goes to electron transport layer ETL, and the top there is a transparent top electrode. So, the hole actually follows the path of whole transport layer, and then it goes to another transparent top electrode here. So, actually this also allows light to fall in the perovskite material. This light actually falls to the perovskite material. So, these are individual layer which play a role in this silicon PSC tandem solar cell. So, now the question, what are reflection and parasitic losses in a tandem solar cell? So, we have seen that we make a tandem solar cell, and theoretically we compute, and we can see that the efficiency goes very high. It overcomes its SQ limit. One can also have almost efficiency of 50%, but there are certain losses in tandem solar cell. Out of several losses, the reflection and parasitic losses are important. Reflection losses, we use different material and different interfaces. Just now we have seen one example from where light gets reflected back. Okay. So, these are called reflection losses. In order to minimize the reflection losses, we have to use some the anti-reflection coating. One typical anti-reflection coating is magnesium fluoride MgF2, which is generally used in the tandem solar cell. And the parasitic losses is very important, because this when we use this configuration, there are several the layers which are there in the tandem solar cell, okay, which generates electron photon which are not used for the for the photon generation, okay, because of multiple layers. So, these are all actually lost, and these are known as parasitic losses. Okay. So, these two important losses are very much evident in case of tandem solar cell, and there are ways how to get rid of these losses, which I discussed in detail during lecture. So, let us again review this entire topic with some typically or frequently asked questions. So, the first is how conduction band of TiO2 nanoparticle gets populated in DSCC and QDSCC. So, it is very simple. So, we know that suppose I consider DSSC, this is HOMO, this is LUMO, and this is the conduction band or CBM of TiO2, this is di. Okay. So, when light falls, the charge carriers are generated, electron goes here and then electron comes to the conduction band edge of TiO2. Okay. So, this is the way the injection is taking place and the conduction band of TiO2 is getting populated with electron. Okay. So, now the second question is identify the reaction step in DSCC for energy generation and dye regeneration. Okay. So, energy generation, what is the reaction step? We know that when the electron are produced here in TiO2, there is a transparent conducting oxide which is connected with that, and then electron follows this path, it goes through the load and eventually it goes to counter electrode. Okay. Counter electrode which is a platinum layer. All right. Now, in between there is electrolyte, which is I minus I 3, this is electrolyte. So, this is the reaction for generation of power, and then this HOMO actually gets electron from the redox level of the electrolyte and the dye regeneration takes place, and again it follows the path from HOMO to LUMO. Okay. So, this is the entire process which is happening in case of dye sensitized solar cell. In quantum dot sensitized solar cell it is almost same, only you replace dyes by inorganic quantum dot. Third question is energy level diagram show electron relaxation path. Okay. So, just now I have shown you the electron generation and relaxation path in case of perovskite solar cell. It is same as or almost similar in case of dye sensitized solar cell. Let me first draw the levels. Okay. This is HOMO, this is LUMO of dye, this is conduction band minima of TiO2, and this is electrolyte, and this is the E redox level. Okay. So, let us just look at the relaxation path here. Relaxation means recombination path. There are generation path and recombination path. So, recombination path is that when an electron falls back to the from LUMO to HOMO. So, there is a relaxation path which is also a recombination path, or electron falls from the conduction band of TiO2 to HOMO of di, or the electron goes to from conduction band of TiO2 to the E redox level. Okay. So, these 3 1, 2, 3 they are the relaxation path in case of dye sensitized solar cell. So, now the question is, what is the role of electrolyte in dye sensitized solar cell? So, we know that dye sensitized solar cell, as we have seen the configuration, that dyes are anchored on TiO2 and TiO2 is connected with a transparent conducting oxide, okay, which also act as a the photoelectrode, and then the electrical path goes and it connects to the counter electrode, and in between counter electrode and photoelectrode we have electrolyte, which is I3 redox couple. And the role of this redox couple is that what we have discussed, it takes electron from the counter electrode and it gives this electron back to the HOMO of dye, and that is called regeneration of dye. This is an important process of the dye sensitized solar cell. Another important thing is that electrolytes actually play a very important role in the entire charge transport process in the dye sensitized solar cell. Okay. So, overall the efficiency depends very strongly on how electrons are getting transported or charges are getting transported through the electrolyte in the entire solar cell. Okay. So, now the next question is how electron mobility influences DSSC performance. Okay. So, we have already seen one particular case study where I have shown that how electron mobility influence the performance of DSCC. So, let us again try to look at what we had discussed. So, if you have electrons whose mobility is higher, that means they move faster. Okay. So, what will happen? They will generate more current in the circuit. So, you can see higher short circuit current density in case of a solar cell when electron mobility is higher, okay, in a dye sensitized solar cell. But when we consider the open circuit voltage, because as the electrons moves very fast. So, this is a conduction band minima of TiO2, okay, and the electron moves very fast, and this is the FTO which is connected. As the electron moves very fast, because its mobility is high, okay, it actually depletes electron from the conduction band. Okay. So, therefore, the Fermi level comes little down and the redox level is here, and VOC, which is actually difference of Fermi level and redox level. Okay. Let me this actually decreases little bit. Okay. So, the enhancement of ISC is very high, short circuit current when we have higher mobility, and there is a little decrease in VOC, which is almost insignificant, but the enhancement of short circuit current density is very significant when we have higher mobility of charge carrier in a dye sensitized solar cell. Okay. So, now why QDs are used as sensitizer instead of dye? So, this is a very important point, because when we use a dye sensitized solar cell, dyes are generally the organic material and sometimes they are not very stable in the electrolyte, and also it has been seen that the absorption is not that good, and sometimes the absorption is almost same as what is the absorption of the electrolyte. So, this actually reduces finally the performance of a dye sensitized solar cell. Stability is a very important issue, and therefore, it is important to look at the inorganic material, and the best choice which people found after dye sensitized solar cell are inorganic quantum dot. So, one way you can have a variable band gap. So, I discussed about quantum confinement effect. By quantum confinement effect, one can see how one can vary the band gap. Also, when we have different quantum dots anchored in the same TiO2, I have variable band gap. So, we have more absorption capability. Along with that band gap tunability, we also have the multiple exciton generation capability in case of quantum dot, and therefore, quantum dots are used, and there is a good replacement of dye. Okay. Now, the question is uptake of sensitizers enhances JSC and VOC both. Okay. Why? Uptake of sensitizer means if you have more amount of say dye, okay, which is sensitizer. So, if you have more number of dye molecule, we have more charge carriers generation, and that is very simple to explain why the current density enhances. Okay. So, now as far as the enhancement of VOC is concerned, as far as VOC is concerned, okay. So, if I have this TiO2 again, this is dye, okay, and this is electrolyte, this is E redox, it is CBM, so if you have more number of dye which is here, it gives you higher short circuit current. This is clear because number of charge carriers will be more, and then these electrons which will be injected here. Okay. So, now if the number of electrons is large, the population of electron will also be large in the conduction band of TiO2, and that will take this Fermi level up. So, again the VOC, which is equal to EF minus E redox, will go up, because the difference between Fermi level and redox level will increase. So, in this case, along with short circuit current density, open circuit voltage will also increase, but it was different in case of when we talked about mobility. In mobility, what we have seen, this short circuit current density will enhance significantly and open circuit voltage will reduce, but the reduction is very small because of the higher mobility of charge carriers. But in this case, both short circuit current density and open circuit voltage will enhance. Next question is, what is the role of mesoporous TiO2 layer? Why not porosity free layer in QDSSC? This is very simple, because if this is mesoporous, we can have large number of dye molecule which can be anchored. Okay. And unless and until we have large number of dye molecule which are attached with the TiO2, we cannot generate the adequate number of charge carriers. And just now I have seen the previous example that one has to look at the capability of having more dye molecules or dye uptake of the solar cell, and if you have most mesoporous, you have larger surface of TiO2 which can have more dye molecules, eventually increasing the short circuit current density, open circuit voltage, fill factor as well as efficiency of the solar cell. So, why generally perovskite solar cells have higher efficiency as compared to other solar cells? So, I told you there are few important properties of perovskite. One is the lower exciton binding energy, second is the band gap tunability, higher absorption and also higher transport. I mean the transport length of charge carrier in the perovskite all actually give rise to higher open circuit voltage as well as short circuit current in case of perovskite, eventually increasing the efficiency of perovskite. Okay. How band gap tunability is achieved in perovskite solar cell, that also we have discussed, that you can tune the band gap, okay, for a inorganic organic halide or a perovskite. Either you change the organic part or you change the metallic part or you change the halogen part. That means AMX3, which is the typical the chemical name of this inorganic organic perovskite, either you change A or you change M or you change X. Okay. All these three examples we have seen how one can significantly vary the band gap just by changing either of these three elements or compounds present in the perovskite structure. How do you select top and bottom solar cell of a tandem configuration? Okay. So, we have already discussed for a top solar cell, the top one is higher band gap and the bottom one is lower band gap, and what we have discussed, when light falls on this, the higher band gap part of the tandem solar cell absorbs a higher energy photons, okay, or blue photons, and lower band gap solar cell which is in the bottom solar cell, it absorbs the low energy photons or red photons, eventually giving the output voltage from both of them from two different spectral level of solar light and giving higher efficiency. What are different losses for a tandem solar cell? So, one important loss is that the reflection loss, which I have discussed, because it is a layered structure and therefore from different layers the light get reflected and therefore a strong anti-reflection coating is required. Another is parasitic loss. The parasitic loss is that there are some material which are having large number, say contact layer or some TCO layer, which are having large the charge carriers, okay, free charge carriers. So, whenever the light falls, the charge carriers are generated, but they are not take part in the solar cell action. So, this is a kind of parasitic loss, and another loss is also ohmic loss, because you have different series and shunt component of the tandem solar cell giving rise the typical ohmic losses, okay, or electrical loss in the tandem solar cell. So, one has to take care of all these losses by choosing proper material, by choosing proper connection, by choosing or adding proper anti-reflection coating, okay, and then one can achieve higher efficiency of a tandem solar cell. Okay, so with all this review question and frequently asked question, this topic 3 is completed, and in the next class we will start the next topic. Thank you.